Hello everyone again. Now that you've learned how to do stub matching, we will just walk through one of the homework problems, 10.33. So the question asks, given a certain Z load and a certain Z naught, where are the stub insertion locations and what's the shortest possible stub length? Let's start with the short circuit version. So I've already written down the normalized load impedance here. You just divide the load impedance by the line impedance, then you have the point normalized to the load, normalized to the line. And on the Smith chart, it would be here. Small z of load equals 0.8 minus j 0.2. From this point, we draw the circle indicating various wave impedances at each location. Try to make this as circly as possible. Good enough. So remember, we take a 180 rotation or flip from the center to get the load admittance, Y load, equals 1.17 plus J 0.3. So that's the Z load or Y load. From here, we will find the first stub insertion location. So we rotate and we reach the unitary circle around here. That's the Y in 1, the admittance of the first intersection with a unitary circle. If we keep going, we would reach the second one in 2. So I'll just write out their values. One is 1 minus j 0.32. The other is 1 plus j 0.32. So we recall from the last video that we want a certain short circuit stub with an impedance that could exactly cancel out the susceptance here. So to find the short circuit stub length, we first start with the short circuit stub location. So this is the short circuit's admittance if it had 0 length, because infinite conductance. If we pick this stub location, Y in 1, if we pick to cancel this one out, then we want a short circuit stub that cancels out this minus j 0.32. And that short circuit stub would have to be as long enough to get here. The plus j 0.32 would cancel out the minus j 0.32. So the length would be all the way between these two. You can read out the actual length in terms of lambda from the Smith chart, but here it's a bit hard to do so, so I'll leave that up to you. That's one possible system to match this transmission line system. But in fact, the book question asks for the shortest possible short circuit stub length. And this is actually not the shortest possible. I'll show you why. Erase that. Because if we pick to use the other possible stub location and insert the short circuit stub there, we would need a short circuit stub that can cancel out plus j 0.32. So we want a short circuit stub that would reach this point. So if we find the length of this, obviously this is shorter than that. Again, it's hard to give you the exact value in this case because it's hard to read off the Smith chart here. But if you actually compute the value in meter, which you are given the frequency to do so, then you will find that this short circuit stub would be shorter than this one. Hence, this would be the answer to the question. B part of the question also asks for the stub length for the open circuit stub. So instead of having a short circuit here, you would have an open circuit here. I'll erase it a bit better. An open circuit stub. And to find the length of that, well, we already know where to start with for the short circuit stub. We start with the infinite conductance. So for open circuit, we actually just start with 0 conductance because obviously in an open circuit there's no current, so conductance is 0. And that's how you do this question at a high level.